Hi, everybody, and welcome to this talk. We are going to be spending some time to think about how to really improve our Rust code. The talk's title is Get Maximum Benefit from Zero Cost Abstraction. I'm really going to try to think about the ways to get the most from Rust while keeping your runtime performance extremely high. One thing to note, though, is that none of the talk is actually completely new. There are some 3 guide places to look for some really useful resources after this. One is the API guidelines, another is the index for Clippy, and then is a repository idiomatic Rust that you can search for. The API guidelines provide probably hundreds, at least dozens of really useful and practical tips for being able to use Rust effectively. Clippy provides a very it definitely provides hundreds and hundreds of programmatic checks for your code. And along with explanations in all of them. So, for example, in this case, we're checking to see whether or not we are comparing for known constants that are already defined inside the standard library. By following Clippy's recommendations, we actually get much more closer to our intent with and we remove bugs from our code. Okay. So now I've got acknowledgements out of the way. I would also like to define zero cost. Magic doesn't actually exist. We can't get something for nothing. So zero cost in the sense of zero cost abstractions actually means zero additional cost. You couldn't have written something better yourself. Possibly a more technically precise way to express this would be to say zero marginal cost. Lastly, I want to also point out that zero cost also relates to runtime performance, and therefore we can trade off compile time execution if it will provide us with faster runtime code. That is, builds can take longer if the program will run faster. Okay, let's start off with a couple of very small, quick tips. Some really useful literals exist in the Rust language. One of them I quite like is the byte literal for being able to encode ASCII as an integer and as a U8 integer rather than as the char type, which takes 4 bytes. If we prefix a character literal with a B, we get a U8 value. So capital A is the number 65 as U8 value. There is a similar way for us to be able to inject Unicode Unicode inside our source code. With the /u, we can add in any code point rather than including the actual source literal ourselves. Okay, so now let's touch on idiomatic Rust. We had a look at Clippy before, but what we really want to do is enable the rest of our team to follow along with our code, and we do that by maintaining the conventions of the ecosystem. Programming is a team sport, and writing software is easier than reading software. So by that I mean it's harder to follow along someone else's mental model or someone else's thinking when you're just reading the source code. In Rust, I would say that getters and setters are kind of generally not useful. We have traits for interfaces. We don't use inheritance. And so therefore, the same benefits, if there were any, I'm not confident that there were, the same benefits of Java-style getters and setters are sort of not available in Rust. There is like all rules, or most rules at least, there's an exception. And that is if you have, let's say, a wrapper type that provides a access to one logical thing, a get or it might be useful. So for example, from the standard library, we have these non-zero types which provide access to the raw value. And cell also does a similar thing. They have a get method which returns the inner type. There are other conventions. I've touched on the API guidelines right at the start. When you are dealing with conversions of your types, you want to use the right method. By that, I mean either as or to or into, depending on how you are performing the conversion, as well as sticking with the conventions of the ecosystem relating to generating iterators over some collection. You should also eagerly implement traits. If your type is able to be compared with for equality with other types, implement partial equality. Implement clone where you can, or partial ORed where it's appropriate, because your consumers or the people that are importing your code cannot implement those traits themselves for your type. It's impossible for them to take a foreign trait like hash and a foreign type, let's say something that you've created, and implement hash for that foreign type. It's to do so, they would need to create a new type around it, and it's just kind of annoying. So where you can, you should implement as much as possible. I want to talk a little bit about actually creating some other practices which will lend themselves to quality software. There are linters inside the ecosystem. We've talked about Clippy before, and to invoke it, we use cargo Clippy. Rust format is available via cargo format inside your crate. For extra points, you can make things harder for yourself by adding a pre-commit hook. This will actually, you could ask Git to run cargo format on your behalf and fail if their formatting isn't correct. In fact, you can ask cargo format to update the code itself, potentially, which may or may not be what you want. So to set up the hook, you first create a file called pre-commit or pre-commit inside the hooks directory of your hidden Git directory. Make it executable, and then Git will invoke it every time you run git commit. Here's an example. We need the hashbang syntax at the start because we didn't provide a file extension. I like to add a comment saying what this file actually does. And I've kind of got a cheat available, which is that if I want to skip any of these checks, I can just invoke git commit with cheat equals 1, and then the pre-commit will pass. Otherwise, I ensure that the formatting is correct. I run the Rust compiler under its check mode, which is a fast version of the compiler, and then I run Clippy, which is a more a lengthier thing to check. So at first I'm checking formatting, then I'm checking that the code compiles, and then I'm checking that the code is ergonomic. If those all pass, I'm allowed to commit my code. Something else which is a little bit more complex, is when you define a function and you are taking a reference to some type, try to remember to take a reference to the borrowed version of the type rather than borrowing an own version. So for example, instead of borrowing a string, we borrow a string, or we take a string slice as an argument. It'll be easier for your callers. It turns out, for technical reasons relating to Rust's deref trait, that if you accept a string slice, you'll actually enable your callers to call your function with a reference to a string, because a reference to a string actually dereferences to an str with a lowercase s. So what we want to do is change this string. And then all we should need to be able to do here is just change string into stir. And then we can now suddenly call is all caps with, oh, that's not correct. And we're done. It's not always going to be this simple. Some other software, some other code will be slightly more complex. The same thing is, just to be very clear, we want to avoid things like taking a reference to a box of, let's say, T. What we should prefer to say is just take the reference to a slice of T. The second form here is going to be easier on your callers and will still enable people who have box the type to be given access to it. Okay. Sorry if that's confused some people. Let's reduce the cost of monomorphization. That sounds a bit crazy. Every specialized function that your code creates, or your compiler creates, whenever you use generics and instantiate, whenever you use generics, the compiler will generate a specialized version of a function for all of its input types. This takes up space. We can actually avoid some of that space by being a bit sneaky. Let me show what I mean. I've got a function here, is all caps, which is actually doing exactly the same thing as before. But now we also want to accept a cow for whatever reason. Just because it's the most, it's the like type in the standard library that is the most fun to say. Now I've got here a crazy looking generic type, which says that I'll accept a reference to any T where the T dereferences to str, to a string lowercase s. This will create a new version of is all caps for all of its input types. What I'm going to do instead is duplicate the function to start with, and then change the one that I want to call to not being a generic. And then I'm going to give it an underscore to indicate that it's private. And then in the public method, although public because I'm not using the pub keyword, although I can, I just call is all caps with the prefix underscore. So now what's triplicated, or if I had, say, a cow and then a string and then a string slice, only this smaller fraction of the code itself is actually triplicated. But there's only one version of the calling of the function that ends up being the body of the work. But there's a trick. We need to ask Rust not to inline the code. Otherwise, this code will all get injected to all of the specific versions of the code that we want to create. So that's good. Okay, so now we have reduced the cost of monomorphization, at least the space cost. Let's talk a little bit about testing. And I say testing generally because actually what I really want to speak about is formal methods. If you have people using your software, you really don't want that software to break. And formal methods, including formal verification, are probably still in the difficult, like in the spectrum of easy to difficult. They're probably still on the difficult side, but they are moving towards easy. Easy may be too strong. They're kind of moving towards learnable. Modeling involves spending time, so we kind of create a specification for how we want our program to run. And then the first step to kind of using modeling is actually to just write a document describing how you want the program to work. This could be called README-driven development. You kind of write the documentation before the code. This gives you time to think it through and design your API without actually having anyone dependent on your code. There are many ways that are more advanced than that, including formal verification and other languages, but writing a document actually will save you an intense amount of debugging time later on. I make that as a claim without evidence. So if you disagree with that, please fire up in the comments. That's fine. I would like to make this claim. A form of testing that's less common than unit tests, but it's still really valuable, is this thing called property testing. In Rust, the prop test crate provides the ability for you to test a range of inputs for functions rather than just one test at a time. Or sorry, a given unit test, instead of giving it one specific input and checking its output, you can just ask for random inputs within inside a range. It's actually very, very interesting and quite revealing sometimes about it finds the edge cases for you. And if you really want to find the edge cases, then you fuzz your inputs. A fuzzer is a program which generates random inputs for your function. Now, this sounds really complicated and difficult. It turns out, though, that fuzzing libraries actually make it relatively easy for you to just fuzz a specific function of your program. And you kind of write these test handlers, kind of like these baby programs that call one function of your API, and then just kind of give it random input, like things that it should never ever appear in practice, and see what breaks. And every time it breaks, your program gets stronger because you fix the problem. You fix the problem, right? Okay, so lastly, maybe not lastly, there's actually plenty of slides to go. The new type pattern is very, very handy, and is very confusing or alien to people who come to Rust. So I've got this problem, and that is we've got two thermometers reading the temperature. And they actually are reading the same temperature. This is 20 degrees Celsius. And it turns out that 20 degrees Celsius is also an integer in Fahrenheit, which is quite fun to know. So this, what we really want when we calculate our average temperature is 20 degrees Celsius. Or 68 degrees Fahrenheit, depending on if you are one of the one countries, I believe, that uses Fahrenheit in the world. Anyway. But instead we get 44. Now this is not a problem with the type system. These are all floating point values. Rust compiler does not care, really, that you've made a logical error. So what we do instead is we wrap F32, or a floating point value, in our unit. Now when we go to compare them, or add them together and then divide, the program will fail to compile. Now you may be wondering, is failing to compile really preferable to crashing? Or no, is failing to compile really preferable? And the answer is yes. Actually, you don't want things to just silently work that are broken. It's better to not have the thing start than to think for something to fall over half the way through, and even worse, fall over without you being ever told, because you get a valid input, a valid output when you try to create the average temperature. You can one subtle way to improve this even further is to say that booleans and options should really be returned from functions. Now, that's because if you assign this boolean from this call to is alive, or it's a method, I suppose, and you would get a bool out, it's true. Later on in your code, you now need to wonder, why do I have a boolean in my code? 10 lines later, it kind of becomes a little bit confusing. You need a variable that's well named, and if it's not, then you've just kind of got a crazy variable that you true or false. What does that actually mean? It's hard to know. It might be you're comparing a quality with something. So instead, we can change from an is underscore method. So that's a method that returns a Boolean. Instead, we return just our own enum. And this way, it doesn't matter where our variable appears, it's always going to refer to, it's always going to be sort of self-documenting. That it's a value that encodes the state of whether or not something is valid or alive or not in itself. Oh, this is actually a lie. It doesn't have self in there. An early version of this slide actually included a type parameter in lifecycle. But then I thought that people might get picky and complain that I also needed to implement clone and so forth. So I should have fixed that up. I like marker traits. So this is a really nice part of the type system and really focuses on this idea of a zero cost abstraction. And that's partially because I think traits are kind of one of the centerpieces of Rust. Within the standard library, you get a small set of marker traits like copy, send, sync, copy, send, size, synced, and unpin that live within the standard marker module. And it's hard to read there, but actually at the bottom it's saying that size is so common that you actually need to opt out of it in your own types. So the compiler will always derive size for you unless you ask it not to explicitly. The idea behind these types is that they are providing information to the type system that takes up no internal representation in the final binary or final executable itself. So they take up zero space, and they are therefore of zero cost in our definition from the start of the page, start of the talk. We can get further with zero cost abstractions. It turns out that using option wisely, if you are dealing with references, is super, super handy. Stupid thing to say. If you wrap a reference type that is a ampersand T or a box T in option, it takes up no more space in memory. That's because Rust guarantees that that references, which are pointers, are never null. So there's a free bit pattern available that can be used for pattern matching. We can make our Rust code easier to use by avoiding a couple of gotchas. We want to avoid magical typecasting with deref. So if you remember a couple of slides ago, we talked about the dereference trait and that we kind of were able to accept multiple types. So this was a reference to a string versus a string slice. And it turns out that you can abuse this to create something called deref polymorphism. It's a known anti-pattern. Now, this is a more difficult code example, but let's see if I can show you what the problem is. So what I might want to do if I was to come from an object-oriented programming language is to kind of use deref to recreate inheritance. So I've got here a base class with a greet method. And then I have a person class that has inside of it a member base. And the deref implementation for person involves returning self.base. So when the person is dereferenced, it returns this base class, and the base class has an object. Now, if I have a main method, I can use some sort of one of the magical things about Rust that is this dot operator implicitly dereferences on demand will enable me to call a greet method from greeter just because person has implemented deref. We do not want to abuse this. It's like a very sharp edge feature. It will cause problems, and it's going to be very, very confusing. We have two ways out of this. We can either use a trait. So trait greet will enable us to say that the person can implement greet and actually rely on the default method itself. We don't even need any extra code. And now we can call greet from person. In fact, we've simplified a bunch of other stuff because we don't need multiple types and so forth. Alternatively, if we really want our base class, if we really wanted to kind of create something which was kind of templated, we need to write the facade ourselves. So we just create a greet method, and then we're given access to the base.greet. You see that the person's greet implementation is just dispatched to the internal class. And now if I have main greeter dot greet does the right thing. It's slightly less ergonomic than breaking the rules, but please don't break the rules. It really will cause problems, I promise. To improve your Rust code, you should make it impossible to create like partially constructed types. It's really tempting to add like an isValid or validate step, but actually doing so will just create mistakes because people are lazy and will forget. People are humans. We can actually encode the validation logic inside our constructors and return result rather than T. This is a form of programming called making illegal states unrepresentable. But in this case, I have sort of a building and a height. Now, the building's height must be non-zero. And what I want to avoid is validation. So in order to get around this, I have some cheater code. In the new method, I'll just copy and paste. And I'll go back a slide. My new method becomes we return result. And if height is nothing, we return 0 height. So I needed an error type in there also. And otherwise I return OK. This makes it impossible for there ever to be a valid building object around that has the illegal type. Now there is a little bit of extra bureaucracy around because we need kind of a result type and we need an error type. By the way, if you have implemented debug, then you've implicitly implemented error as well because there's an automatic. But that is, and this isn't spelled correctly. But this will provide us with significantly stronger, more robust software. I've got a couple of other pieces of advice before we wrap up. You've probably heard of generics, which is static dispatch, and trait objects, which is dynamic dispatch. But I'm here to tell you today that there's a third way called enum dispatch. We create an enum type which kind of encapsulates all the possible states or all the morphisms, all the types that our thing could be, and then we match on it inside the calling code. The downside is that it becomes slightly unwieldy to use. Inside the functions that make use of this kind of super type, you need to match on every single instance of it. Now, to make it smoother, there is a crate called enum dispatch, which takes a lot of that pain away. it's much, much faster. And some of the benchmarks that this provides, we're talking about sort of 10 times performance gains, even inside the static dispatch case, which seems kind of crazy, but I encourage you to take a look and see. If your trait has more than 2 or 3 methods, there's probably an opportunity for you to refine your design. There are very few traits inside the Rust standard library that have more than one method that you need to implement. When they do have multiple methods inside the one trait, a lot of them are provided via default implementations. If you have a trait that is very narrow but deep, you'll find that it's much easier for your callers to make use of versus an API that is kind of broad but shallow, is more specific, it's not general enough, and you'll find that it's really difficult for people that are using your trait to make use of. That's everything that I have for you today. I really hope that you have enjoyed the talk. Hopefully, I've said a few things that you've agreed with, a few things that are new, and possibly even a few things that you disagree with. You are very welcome to say hi in the comments, and let's see if we can start a discussion. Hit me up on Twitter, and let's see where we can go. Take care. Bye-bye.